Right, welcome back. It's been about a year, but the pendulum design turned out to be harder than I thought, and after numerous attempts and failures, I decided to take a break. And the good news is that there was a eureka moment a few weeks ago, so I've made a new mechanism and I'm now working on the software to drive it. Now, there's still a chance it could fail, but if it works, the results will be in the next video, so keep your eye on this channel. And this video is just a catch-up to show the latest design and why the first one failed. As mentioned, the pendulum is free running. It's not used to control the timing, but it does need some method of keeping it swinging. And whatever system is used, it has to be self-starting in case of power cuts. The overall requirement of minimal maintenance also needs to be met due to the position of the clock. This means no electrical contacts or switches, relays or DC motors with brushes if possible. So the original plan was to drive the pendulum directly with a stepper motor mounted between plates 4 and 5. And here's the first prototype with just the motor clamped to a shelf. This is the front view. The metal bar is a conrod which is fixed to the motor spindle using a flange, and the lower part is bolted to the rest of the pendulum, a lump of wood in this case. Here's an overhead view. You can see the rotary Hall effect sensor at the end of the motor spindle, just like the motors for the clock hands, so the controller knows where the pendulum is at all times. Now, the controller pulses the motor for a few steps to give the pendulum a kick at regular intervals, and then power is removed from the motor to let the pendulum swing back. Now, there is a small resistance from the motor's magnets even when no power is applied, but the momentum of the pendulum is enough to overcome this. Now, a major advantage of this method is it avoids all external components. And some electronic pendulum designs use an electromagnet and a sensor at the bottom of the pendulum, so this method avoids all of this clutter and its associated wiring. And a further bonus is that no separate axle is needed. The motor spindle is already supported with ball races within the motor body, and these seem sturdy enough to support a pendulum. Now, I had high hopes for this method, and the motor certainly kicked the pendulum okay, but it failed to stay in sync and the swing never built up. Now, it took some head scratching to realise that when the motor was freewheeling, the pendulum was moving it back to an undefined step position, so when pulses were reapplied, it would rotate in the opposite direction, sometimes, and this damped the swing instead of prolonging it. Now, I couldn't find a solution for this, even by using the sensor to detect valid step positions. Maybe I didn't try hard enough, but either way, I moved on to try various other methods, still within the clock body, such as solenoids, electromagnets, and even bought some wire to wire my own. But by then I'd had enough and moved on to other projects. The recent breakthrough was to go back to the original stepper motor idea with all its advantages, but use an additional driver bar to decouple the motor from the conrod and hence the pendulum. This meant the motor could turn the pendulum, but the pendulum could not turn the motor. These are the customary outtakes for the new driver and conrod, but I eventually settled on a workable design. The driver and conrod both share the same motor spindle, and the driver pushes the conrod using repelling magnets to avoid any points which would wear down over time. These are the magnet holders. They're separate pieces to avoid having to recut the larger parts if the design changes. Here's the conrod showing the two magnet holders fitted and the central ball race. This allows the conrod to swing freely on the motor spindle. Now, the spindle is quite short, so I had to mount the motor on small plates to maximise the amount available. And here's the conrod mounted on the spindle. The controller just needs to know a couple of positions for the pendulum, the rest position and the maximum swing, so there was no need for a rotary sensor. I don't think there would have been room anyway. So a couple of simple sensors will do. And to amplify the movement, the sensor magnet is mounted on an extender bolted to the conrod. The kink is to avoid other components, so again, making this a separate piece means the angle can be changed without recutting the more complicated conrod. Here's the driver with its own sensor extender, and this is with the magnet holders fitted and the central flange which is fastened to the motor spindle. And finally the complete mechanism fitted to the motor. This is plate 4, which has now been reassembled and fitted to the rest of the clock engine. The lower sensor indicates the driver's home position. This is so it can back off to a known position after kicking the pendulum. The sensor at top right indicates the maximum swing position for the conrod, and the other indicates the rest position. The controller can use this to detect if the pendulum is stationary, and if not, it can use it to time the swing and calculate when to kick. And the plan is to make the system self-calibrating, so it's independent of the pendulum length. Okay, that's the theory. I now need to connect the motor and sensors to the controller and write some code, so it may be a while. If you're a whizzo at pendulum ballistics and fancy having a go at designing an algorithm using these sensors, please let me know. As a guide, the target pendulum length will be about 2.5 meters. The total swing is 23 degrees, giving a swing distance for the bob at the bottom of about 1 meter, although this may be reduced if it's too distracting in the lounge environment. Fingers crossed, and hope to post a follow-up with some good news. See you then.